Phil Shillett and Ian Smith from Intel Research. Ian is based out in Seattle, and Bill is up there, and a lot of times down here. They're going to tell us all about location information, and hopefully you should be thinking about ways that maybe we can collaborate with them and do some interesting stuff that only we and Intel could do if we're working together, because I think there's some interesting possibilities in that space. So, go ahead, Bill.
Okay, thank you. The title of the talk is Bootstrapping Location on the World Wide Web, and a lot of this work is being driven out of our Seattle lab. Anthony Lamarca is the PI on this project. Anand Balachandran, UC San Diego graduate who worked on radar at Microsoft as an intern. Yatin, a systems researcher from AT&T Labs. Ian here, Park guy and Georgia Tech guy who's now at Intel, working on some of the privacy issues, and a slew of other people. And we're doing this project in an open collaborative style, and we're working with universities, and I'll talk more about that in a minute. So first, a word from our sponsor, Intel Research. I want to give you the sort of the background for why we can do this style of project. I want to describe the organization that we're a part of. So Intel Research is doing off-the-roadmap research, sort of like off-road vehicles. And one of the ways that we're doing this is collaborating with key universities. And we have these organizations called lablets, which are university-affiliated Intel research labs. They're co-located on the campuses of universities. And we've forged an agreement with the universities to say the intellectual property that we create inside these lablets is going to be open. It's going to be public. It's not going to be things that we patent and we strive to make money on. So it means that we have a real free flow of ideas. It means that faculty can come into the lab, grad students can come into the lab and talk over ideas without having to think about patenting first. Intel Research also has alignment with funding of researchers, university researchers and grad students. We also have projects inside of Intel, so when we have some intellectual property that is closer to the core of Intel, we create these projects inside. And Intel Research also has a means of funding for research purposes companies through Intel Capital. I mentioned these lablets. There's 4 of them currently. These are co-located at major universities, Berkeley, University of Cambridge in England, Carnegie Mellon, and our dear own University of Washington. That's where a lot of this work is coming out of. James Landay is the director, and the style of these lablets is that we get an academic, somebody from the university, to take 2 years off from teaching, come and sit in the lab, bring their grad students into the lab, bring their collaborations with their fellow faculty, bring those connections into the lab, and sort of drive a research agenda with Intel researchers who are also sitting in the lab. So we try and get a balance of about equal parts of university grad students, master's students, faculty, and Intel. We call them blue badges because our badges are blue. So I want to give you the 1-minute version of what we're trying to do. We're trying to provide virtually free client-side, which means private because there's no infrastructure tracking, almost global positioning. And we're doing this by listening to the unique beacons that come out of Wi-Fi access points. And some people know this very well, that access points beacon. And so the question is, how good can you do? Well, if you look around or use tools like NetStumbler and look around, you see that the density of access points is great in many urban areas. And so this is the basic idea, is that we have a mechanism of, this mechanism exists already called war driving, which is mapping out the geographic position of these access points. Each access point has a unique MAC ID. Once you have this map, you store it on your device, either your PDA or your notebook computer or even your smartphone. And then, let me try and get the demo up here. And then when you move around, there's no movement going on. Hang on a second. So this is a war drive of the area around Google that I did yesterday, a couple of days ago. And basically what it shows you is that as you move around an area that has access points, you listen to the access point beacon, you can look up the GPS coordinates of this access point, and now without having a GPS on my device, I know where I am. I roughly know where I am. There's actually a visualization here that gives you some indication of the accuracy. Sometimes it gets very large, the precision gets very large, and sometimes it's pretty precise. That's one of the research topics that we're working on, is how to make that better. Okay, so that was the 1-minute version. What I want to give in this talk is sort of the running leap at that story. Why we're doing that, how we're doing it, where it's going to go. I'm going to give the historical perspective, and Barry Hayes is going to love this. So it's all about ubiquitous computing at PARC. How does this infrastructure that we're building work, the architecture? Talk a little bit, bring up that visualization again and talk through it, what's going on behind the scenes there. And talk about our toolkit and sort of the research thrust that we're following. So way back, almost 10 years ago, I worked on a system called ParkTab at Xerox PARC with Roy Want and Mark Weiser and others. And it was a little handheld computer. And what was interesting about this handheld computer is that it piggybacked location on the communication channel. So it used these infrared Death Stars, that's what we call these things, as a transceiver, a transmitter-receiver. You put one of these transmitter-receivers in each room. It was infrared, so it didn't pass through the walls. You put a few of them in the hallways, and then when you use this device for communication, you also knew which cell you were at, the cell being the room. So it was this way of adding location to computation. And so we built this system as sort of an exploration into ubiquitous computing to ask the question, what's different, what infrastructure is needed, how would you use, what applications would you develop, and how would you use it? And basically, we developed this way of interacting with the physical world when you knew your location. So you could pull up your ParkTab device and get information that applies to the current room, which might be a meeting room, so it might be the schedule. You could use it to control devices. We had it controlling these large displays called live boards, and also making the environment responsive. There was a project controlling sort of the HVAC, the shades and the air conditioning in rooms. And we also used it as a way of communication, so connecting people to other people. You knew that somebody was at the coffee bar, so you could go and find them. We had sort of an active badge model here. And so we developed this notion. It's come to be called context-aware computing or location-based computing. And so here's one of the apps here, which is a location-based file system. And basically, the way this device, the ParkTab, worked is it was really a terminal onto your Spark station that was sitting in the office. So it felt like you had a Spark station in your hand. You had all of the connectivity of the internet through the Spark station. And what we did here was we had a view onto a file system where each directory was named as a room. And when you pulled up your location browser, it would connect you to the current location. Another widget that we developed was this proximate selection widget, and this is a list of printers in our office place, and basically it ordered the list by how far away you were. So this was the first device, first handheld computer that integrated location and computation. These were some of the apps that we were developing. One of the big things that came out of this work was privacy. And so, here we were, researchers working on this notion of context-aware computing, and then we would go and tell the world, and the world would respond by saying, "Oh, Big Brother," Orwellian track people with active badges. So basically, techno-weenies like us really love this stuff, but then when we tried to get real users engaged, it was a nightmare. And, rightly so. We hadn't been doing research in the privacy aspects of location. We were doing the sort of basic research and the capability. That's one of the things that has, I think, changed over the years is people are more and more attuned to this issue of privacy. So one other example from sort of the historical archives is a project that was going on at UW about the same time called Mobisaic. This is in the time of Mosaic. And this is Jeff Volker and Brian Bershad. Basically, location-enabled a web browser. So we had this device, and here they're looking at information services. How do you add location to information services? And the way they did that was they had this notion of dynamic URLs, and anything with this $sign, it was sort of like a shell environment variable, would get substituted with the value. And so when you went and typed in this URL, all of a sudden it would substitute your current location. And the other thing that they did that was really cool is they had this notion of scripts. Now, they should have patented this at the time. They had this notion of scripts that you could put inside web pages in the comments. And basically what they did was whenever a dynamic environment variable changed, like your location, they would reload the web page. That was sort of in the script control. And they have some examples in their papers about using this to find the nearest bus stop, nearest appropriate bus stop, and they sort of keyed it into a number of different environment variables. So this was cool stuff. The location-enhanced web at the time, 94, didn't really go anywhere. And that's what I want to talk about is, why haven't sort of location-enhanced devices and location-enhanced information services converged? We sort of see location-enhanced devices, mostly things like GPS-enabled devices, having a trajectory. There's all sorts of, this is my favorite. It's never lost, but I call it rarely lost because I still get lost even when I use that Hertz GPS device. There's fish finders. There's walkie-talkies that have location. There's, of course, GPS devices, and there's cell phones that have location. Pretty much, sort of the appliance model, the single-purpose model, not so much general-purpose computing. On the other trajectory, we have things like information services that we're seeing that are getting more and more sophisticated with location. MapQuest, of course, wayfinding apps are big. Yahoo Yellow Pages has location. One of my favorites is the Department of Transportation in Washington and Seattle area actually will show you where all the traffic jams are so you could coordinate your drive. CompUSA has, when you go and you buy something from the CompUSA website, you can type in your zip code and it will tell you if a store nearby has it to pick up. So it's sort of tying in location with information services. And of course, there's Google Local, which is one of the better examples. So for the most part, information services and devices haven't really converged. And we made a challenge recently to the research community to drive them into this convergence. We said, you guys are working on location devices in the labs. The world has, location information systems. Can we, take this stuff out of the laboratory and try and make it work in the real world? What would it take? And the idea here, this was a challenge we made at a MobiCom workshop in September. The idea here is really simple. If you think about technology adoption, there's this invariant here, which is that the cost of the technology has to be lower than the value lower or equal than the value that the user gets for it. So, this is the traditional one that people want to charge a lot for technology, and so you need a killer app, right? There's an alternative here, which is that you can say, well, instead of having a killer app, if we just charge a really small amount, for the technology, then it doesn't have to be a killer application. It can be, just sort of like a misdemeanor, jaywalking kind of application. And so that's what we're talking about here, is that to make the barriers to adoption, the cost, cost has a number of factors. One of them is money, right? Another is the inconvenience, the confusion, and the weight of the thing that you have to carry, set up. All these things are costs. But if we make the costs and these barriers very low, then we can start seeing some applications and user value that doesn't have to be huge to get adoption. And that's what we're talking about, broad adoption by lowering the cost. So the goal here is to bootstrap location plus computing together by reducing the cost of adding location to devices. I mentioned Wi-Fi positioning is the way that we're doing that. The assumption here is that most people already have Wi-Fi devices, Wi-Fi in their mobile computing devices. So we're not talking about spending extra money here. We're talking about just adding a little bit of software. So our objective is to build a positioning system that's wide scale. It works indoors and outdoors. It can be used everywhere. It has this privacy, observant capability. Privacy is another barrier. And it has, other low barriers to participation. And we're doing this by partnering with university and industry research labs, try and get this thing out there. So I mentioned that Intel Research does a lot of these open collaborations. We have an open collaborative agreement with the universities that we partner with. So this project is very much in that style, open collaboration, open source, open data. Part of this has data. And also open courseware, because we're working with universities that are teaching classes using some of this, this toolkit capability. And one of our objectives is to grow the community, the adoption community here, across many different campuses. So we're partnering with universities, bringing location into these campuses, and then letting the applications that are being developed at UW be run by people at Dartmouth. The applications that are being developed at UCSD be run by people in UW. And all this is possible because it's on top of the web. It's just basically a web page that you reference, a location-enhanced web page. So how does it work? I'll get in a little bit more into the details here. This is downtown Seattle, yeah. And this is a while ago, right? This is a time of UbiComp. So there's a conference, UbiComp, in August, September. And we had a working demo of the system. Basically, it was a conference guide. It was some software that you loaded onto your notebook computer, and it actually ran a local web server so that you didn't have to be connected at all to the internet. You could just use this local web server. You pulled up a web page. It would look at the access points that were nearby. It didn't have to connect. It would just listen to the beacons. And then it would put up web pages that were interesting, facts about the coffee shop that's there. And there's lots of coffee shops in Seattle. Most of those dots are probably coffee shops or some public artwork or what have you. As I said, these access points are all generating their unique IDs. So something about Wi-Fi and the access point beacons is, with the virtually free positioning, you get what you pay for. So this is an interesting diagram made by a research group, University of Kansas, and it shows the, sort of the Wi-Fi signal strength of a single access point. And some interesting things here is that, it's about a block, maybe 2 blocks in places. It's non-uniform. I mean, it's a weird shape. And obviously it's a weird shape because radio doesn't travel well through some structures. I think there's some solid buildings here. So I wasn't part of the group doing this in Kentucky. Where is it? Lawrence, Kansas. But it looks to me like there's some solid buildings here, and probably those are indeed dead spots. I mean, this is some of our experience also, is that, you know, the physical structures change. So one of the things to note here is that, you know, it's not like a precise technology. And because of that, a lot of the work that has been done in robotics on statistical methods, particle filters is one of these statistical methods, are really good to apply in this space. And that's one of the techniques that we're using that sort of helps us deal with this uncertainty. So one of the sort of principles of this idea is that you have a map of all of the access points in the world, that you actually know where every access point in the world, or maybe not all of them, but a large number of them. And, you know, that is a challenge. So we have this joke that even if we paid all the grad students in the world to go around and war drive, you know, you still wouldn't get a complete map of all the access points in the world. And part of this is because there is no real ground truth. It keeps on changing. You know, the students in university, they go back home, they graduate, they take their access points with them. Companies move, new things come, things go. So, yeah. So how do we get this global map and keep it up to date? That's really one of the challenges here. What we're talking about doing is we're leveraging a community that's already doing this kind of activity, which is the war driving community and Wi-Fi clubs. I'll talk a little bit about what that means later. And the other thing that we're doing is saying, well, you can't, you know, get all the information from here. So can we just use regular users with their Wi-Fi notebooks and PDAs who don't have GPS to contribute? And there is a way to do that, and I'm going to talk about that as well. So some information about war driving. Yeah, it's amazing that a lot of people are doing this. Basically, you take your notebook computer or your PDA, you run some software on it. NetStumbler is one of the better known bits of software here. Attach a GPS unit to it, attach a Wi-Fi card to it, and then drive around and map out access points. Associate a GPS coordinate with the MAC ID. Generally, you're also storing other information, like whether it's web encrypted, the SID, you know, sometimes the channel that it's on. And one of the interesting things here, this is just my estimate. This is like a lower estimate, that in the last year, these enthusiasts have gone out and mapped out over 800,000 access points in the U.S.
Yeah, but that could just be the coffee shops in downtown Seattle.
Yeah, right. That could just be the Starbucks in downtown Seattle, right? Yeah. So, so there's a lot of you know, this map information that's out there, and it's not that hard to get. So I want to just point out what's the difference between what we're talking about in war driving, and, you know, the technology is the same, but the communities and the purposes are different. So I just want to point out that we're not necessarily the same, proposing or promoting the same activities as war drivers. What war drivers, for the most part, and not everybody, but for the most part, what they're interested in building up this database for so they can ask the question, here I am in Mountain View at this intersection, where can I freeload? You know, where's a place that has a public access hotspot, or where's a place where they just forgot to configure their access point properly? Whereas what we're trying to ask the question is, I hear some access points, where am I? We're not talking about you know, taking over somebody's access point.
Is it also the case that even if there's a properly configured access point, that you
Yes, the MAC address, yeah, yes. They are. Yeah, actually, since we're talking about war driving, let me just show you this wonderful, here it is. Here's NetStumbler. So this is Marius's app that's showing these access. I'm just sitting here, and this is the access points that I hear, or that I have heard over the last couple of minutes, in this one location. I don't know, there's probably 15 of them now. And you can look at any particular one and sort of see what kind of signal strength you're getting out of it. It's fascinating. It really is. It's amazing that you guys have so many access points. What? Generally, laptops are not... Yeah. So generally, laptops are not configured to emit a beacon. They're not put in infrastructure mode. So you generally don't see laptops. Although some people do put their laptops in infrastructure mode, and some people pretend to be access points, set their SID to T-Mobile and go into a Starbucks and see what they catch. But, you know, that's one interesting thing about this database, is that those people that have mobile devices that are moving access points, or those students who go home for the summer, you have to take that into account. So you have to sort of tag the entries in the database with a confidence of its, you know, steady state, that it really doesn't move around regularly. Another thing that's happening a lot is I think Caltrans now has Wi-Fi access points on the trains, and Boeing just made an announcement that they're putting Wi-Fi access points in their airplanes. So it gives a whole new idea, or, you know, points of reference. You know, where are we talking about the location? So, should I save this? So I want to just show you the visualization I started with, because it brings up some interesting points about how we're doing this. So I showed you the area around Google. I'll show you the area around the Seattle lab. And basically, what you need to do to enable this capability on your notebook computer is you war drive an area, and then you pull that data onto your notebook computer. So this is not talking to any service out there. It's all happening locally on the client. And so this is the area in Seattle that is the Intel lab and part of the campus. And Anand drove off the map, but he's going to come back in a second. And you can tell that, you know, there's a fair amount of density. So I mentioned that, you know, the shape of these access points is irregular, and the precision is what you pay for. So, what I want to show you here is this method that we call particle filters that Jeff Hightower, Dieter Fox, Henry Kautz, these are professors and grad students at UW, have really pioneered. It's a method of statistical processing to find out some estimation of your location. This circle here is a 95% confidence that you're within that circle. And what happens is if you stop seeing access points, the circle grows. We're using this particle filter model, if you know what that is. It sort of the particles disperse over time. So you basically not only know where you are when you have an access point that you're listening to. If you hear 2 or 3 access points, you know even better where you are. If you're not hearing any access points, you sort of know where you are modulo the motion model, which tells you that you could only move at, you know, less than 800 miles an hour or some such. So I guess, you know, what I'm trying to say here is that you not only need to know, you know, your location, but also this error model, this estimation model. It's key.
And this is just purely X, Y. You're not taking into account things like I'm likely to be on the streets, and
Yeah.
5 points are likely to propagate down streets better.
Right. I'll actually talk about that in a little bit. That there is another bit of research that's doing exactly that. Yes. Yeah. So I guess another thing I should say is that GPS is using time of arrival. What we're doing here is signal strength. So basically, you listen to the signal strength of all the different access points, and then you can compute, your likely location by noticing the multiple signal strengths from multiple access points.
Latency be a little better?
Wouldn't?
Latency? How long it took to...
Yeah, time of arrival. Yeah, so it would be better. And the only problem with that is that it's one of these bootstrapping problems. You have to go and change all of the access points in the world to have this new feature, which would be something to measure precisely this time of arrival. It's not something you can just, believe me, it's not something that you can just do in software. Hardware is involved. So if you're interested in that, there's a company called BlueSoft that is creating silicon chipsets, Wi-Fi chipsets, to do time of arrival. I could point you at the webpage. That sort of answer your question?
Yeah, it just seems to me that there might be something that's already there that you could make use of. You can't ping an access point, but there might be a way to find out when, if there was if you were actually in contact with one.
Right. Right.
Then instead of just listening, look at the loop.
Yeah. So, it all comes down to the fact that the speed of light is really fast. Radio waves propagate great. Yeah. And getting that timing, precise enough is difficult. But just the fact that you hear it, is something. Signal strength is something else.
The resolution on your signal strength is not that great either.
Right.
So I think that you can get better resolution on latency because we do have nanosecond timers in place.
Mm-hmm.
Within a foot.
Mm-hmm. Mm-hmm. Yeah, so these are, great things to sort of add to this system. And one of the things that we're incorporating is this notion of multiple sensor models. So you basically, if you have something like this time of arrival, you add it to the particle filter model. If you have a GPS device on your notebook computer, you can add it to your particle filter model. And basically, you switch between the sensor that gives you the best reading, or you combine them.
So if you're lucky, there'll be some access points that are open.
Yes.
And in that case, you could do some pinging.
Yes. Although, I'll get into the, offline, I think I'll get into the discussion about why that really isn't precise. It's just that, in a millisecond, you have a large distance, right? Yeah, but in the future, very much we see that this is a capability that's going to roll out into, if location is a desired capability, if people start using location-based applications, then you're going to start seeing more and more access points capable of doing the precision time of arrival. So generally in this talk, somebody says, but why don't I just use GPS? And, what I want to point out is that, GPS is wonderful. We like GPS, but it doesn't tend to work in many places where people spend their time. It doesn't work indoors. It doesn't work well in urban canyons. And the other point that's really important is that we're talking about making a service or a capability, positioning capability, really low cost. And you can't start off the bat by telling people, go out and buy a $100 dongle to do GPS. And they're going to say, well, for what, why am I doing that? Why, what's the application? You'll tell them, well, it's Google local search, and they'll say, well, I don't understand what the value proposition here. If instead you tell people, we want you to download a little bit of software that might be in a toolbar-like thing, No big deal. It's going to look at the same things that your auto-config in Microsoft Windows looks at, and it will give your position. Then I think the value proposition or the adoption is much easier. The other thing to note I mentioned is that we have these sensor fusion algorithms. So if you do believe in GPS, if you do carry a GPS-enabled device, your cell phone has GPS or your PDA has GPS or what have you, then it just sort of merges into these algorithms. So some of the architectural components going on here, the system consists of stuff that runs on your mobile device and stuff that exists in the back end. The idea here is that war drivers or other kinds of people will provide map data, this GPS plus Wi-Fi MAC IDs, into this back-end mapping service. We call it a user-contributed service. It's sort of like the CDDB, the idea that a lot of people are contributing a little bit of information for the benefit of the whole. This service then sort of munges this data and produces an aggregate map of all the access points in a region, either in a large region like North America, or it could be in smaller regions like states. And this is downloaded maybe once a week or so onto your notebook computer, onto your PDA. And the reason it's downloaded is because when you're moving around and asking for your location, you don't want to go back into the infrastructure and say, where am I? That would basically turn it into a tracking service rather than a handheld positioning service. And then you have either applications, web browser-based applications, or some applications that run locally that interact with this toolkit that we have that sort of give you this location-enhanced web experience or location-aware application experience. Some of those applications might then choose to go out into services, web services, web pages, and provide even more value, real-time information, search results, or what have you. Yeah?
Have that nice map with points for all the Wi-Fi access points, but you also
They're not points. Right.
So I'm driving around and I have nice, accurate GPS data. I know
Right.
that somewhere maybe 2 blocks away is the Wi-Fi point.
Right.
How does that turn into more accurate data? How does it let me actually?
Ian said he'll
There is an algorithm that's just too complicated to explain right here.
Got it.
You got to have a model of the uncertainty, basically.
yeah.
Okay.
So we have this toolkit, basic capability of Wi-Fi positioning. We're distributing it. We're building it as a way of fostering application development, working with our university collaborators, working with other research labs, and also to foster research in location-enhanced computing. One of the problems we've seen in the research world is that each little research group has their own application, and they're unable to share that application with larger user communities. So that means that nothing really ever emerges from these research groups because they only have the experience of 3 people who built the app. It was a good app, and then somebody else writes a paper. Oh, it was a good app. But they have no sort of way to get traction or no way to do comparative analysis. And what we're trying to do here is distribute this toolkit as a way of sort of bridging these different research groups. The software consists of what we call Wi-Fi spotters, which is essentially a component of war driving. It's, you look at the Wi-Fi card and listen to beacons. It has this particle filter-based trackers, which is one of these statistical methods I mentioned. And it has some glue to do the good stuff. Like currently we're shipping it with a web proxy, which sort of sits in between you and the web and adds the location information downstream. So the data, we're also providing, we have a website and we're providing sort of sample data sets and some maps of selected regions. One of the big applications in knowing your location is showing a map of where you are, and you can use it for wayfinding or other purposes. We also, one of the things that we're doing to build these communities in the universities and with their partners is, Intel is a hardware company, and so we've built a little device. This is a war driving device. So it's an X-Scale processor. It's like what you have in a PDA or cell phone. It's a Wi-Fi card, flash memory. It boots Linux, and it has a GPS dongle. And the interesting thing here is it also has a mercury motion switch. So when it's sitting still, it goes to sleep. So Linux suspends. When it starts moving, it wakes up and it starts taking readings. And so carry this around with you, put this on your shoulder, put this in your car, or what have you. And you basically have an easy way to collect the war driving data. The way it uploads it is it, again, uses the Wi-Fi. So when you come back home at the end of the day, it notices the SID or the MAC ID of your access point, and it uploads that data. And so we're distributing these to our university partners as a way of getting them to easily map out those campuses and get some data.
Before it falls asleep, does it at least integrate a few more GPS things to get you more accurate position information? As long as you're stopped.
It's like 40 seconds before it goes to sleep. So
Yeah. Yeah.
I mean, I can get my
Right.
location to within a meter or two if I let it integrate.
Yeah. So it's really new stuff. That's all I could say. It's like, we're still getting it up to that point where it's going to do this. And I think, there's going to be a number of stumbling blocks like this one that you mentioned. But it's on the trajectory. Yeah.
Problem with proprietary maps?
Yes.
So how do you get
Ian can talk about that. Turn on your mic, Ian.
I've lost my mic. There's a lot of problems with the maps. I don't want to go into all of them. Let me give you a couple of simple answers. One is our data set. We have gone to quite a bit of trouble to try to prevent people from putting in proprietary data, and we've already had some conversations with some people who own proprietary data sets to try to get them to contribute those to us. The reverse problem is actually more difficult, which is if you are a large corporation in Silicon Valley who has hundreds of access points, you might prefer to not have your access points in our database, just on the grounds that it's my access points. And so we're currently the process of trying to figure out ways that we can accommodate large organizations who would like to maybe not be in our database or control what is put about them in our database.
Right.
And
So
we're working on that.
there's two kinds of maps. There's the Wi-Fi maps, the access point maps, and then there's the street maps. Were you talking about street maps or street maps also? Yeah. So street maps also has a problem. Basically, there's lots of interesting little glitches in this project. Street maps, which Ian is also working on, has a problem because most of the street maps that are out there are not sort of public access, public domain. The project doesn't absolutely depend on street maps. It's more about a positioning coordinate. And so, we're talking about either connecting to a map point-like server on the web, which is, I think, what we're currently doing, or pulling some of those maps for small use. Or there is Census Bureau map data that's available in the U.S. There's a very U.S.-centric point of view.
So it seems like the key to this whole thing is that you're leveraging this existing resource of war drivers
Yes.
and their ethic.
Well, it's leveraging the existing infrastructure of access points. I would say we could actually do it without leveraging the war drivers.
And that might raise the cost above what it would be to have anyone buy a GPS or something like that. So if you expecting everyone else to build their web apps around this, it seems like the underlying foundation that if the war drivers for some reason were to stop driving, that the whole system would break. It's out of your control.
Right. So I'm going to talk a little bit. Yeah, I have a slide on that, on how to keep it growing even as the number of access points increase and maybe the war driving community decreases. So I have a slide on that. So just to point out the toolkit components, there's a component that listens to the access points. This cache. We're calling it a map of the access points to GPS coordinates, lat, lon, out. A tracker, so this does a statistical processing and actually figures out where you are. There's some computation involved there. And then there's different paths to get this stuff into useful means. One of them is to connect it to some maps, some GIF files or some other representation of maps and display it. Another way is to connect to services, doing through a web proxy, or you can also do it through a toolbar. Currently, we're using a web proxy. Okay, so I mentioned, we're leveraging this technology that we have. Intel has developed this we call it Personal Server Roy Want project. Roy Want, another ex-Park person, and basically, it's this very small, self-contained computer that has no UI to it at all. That's the big differentiator. So it really is a server, and it communicates by radio. And we've added these different components, the Mercury switch, the GPS unit. So the toolkit is currently available for 3 platforms, XP, Pocket PC, and Linux. Written in J2ME, and Ian can give all sorts of details about how this works. He's done most of the work, or a lot of the work. We have it downloadable at our domain, placelab.org. And we also have this way of uploading data and adding to this global Wi-Fi map. So I want to mention briefly some of the research thrusts that we're working on. Intel Research Seattle is distributing this toolkit, but we're also working on some research problems around this. And we're also engaging university researchers on some of these problems. So these are some of the, more interesting ones. I think I have a slide or something to say about each of them. So privacy and trust, as I mentioned, when we developed the ParkTab system, it was great for us systems weenies, but then when we tried to get any users to think about using it, there was this huge shock about privacy. And one of the big things that we want to solve in this system is a privacy-observant location system. And so here, this is, in my mind, the big difference between what people call tracking systems or location systems and positioning systems. So a positioning system is like a GPS unit. It's handheld, self-contained. It doesn't talk to anybody. It listens to the satellites, and it finds out through its own little processor where it is. Tracking system, or sometimes location systems, use network infrastructure. So E911, the handheld cell phone location system, generally is talking to cell sites, and those cell sites and the service providers are sort of computing where you are. So the first thing to point out here is what we're doing is a positioning system. So just by virtue of having all the computation, all the data, all the information on your local device gives you a big leg up when it comes to trust. And the other thing that we're talking about is that eventually you probably want to connect to some location-enhanced web service, in which case we have some models of how to manage that relationship of what you're revealing to that web service, that you give users visibility over revealing that they're in a certain city, or they're in a certain zip code, or they're on a street, and you give them a lot of control over that. I should point out that location-enhanced web apps are only really one kind of application framework to go after. There's also just local apps. I mentioned that we had a UbiComp conference demo, conference companion. It all ran locally, in which case it was not talking to any web service. There was no way, really, that it was revealing your user location. So this is a whole class of applications that give you additional privacy. There's other issues around privacy. which is that the people that are doing the war driving, once they upload their data into some service, conceivably they're revealing something about themselves. They're revealing, where they've been, especially if they do this war driving as a part of their daily lives. They're revealing where they go and where they've been. And I'm going to talk a little bit about distribution for trust. It's sort of how to address this issue of the privacy of the war drivers. There's another privacy issue that comes up. People don't often think about this, but the access point owners themselves may not want their access point mapped. And I think particularly if you're using it for that war driving use, which is where can I freeload, people may be concerned. And we're managing this through a number of methods, but basically propagating sort of a minimal set of information so that you can't really use it for nefarious purposes. So here's where you were asking about the models of GPS. So one of the things that we've noticed is that just the radio frequency signal strength is not all that good for mapping. So a project that's been going on in the Seattle lab with Don Patterson, who's a grad student, Dieter Fox, and Dirk Hennel, another grad student, is looking at applying other information to these GPS Wi-Fi logs. And so I think we have like a little step through here. So when you war drive, you may get GPS sightings that look like this. Here's a sighting, and it has an access point and a signal strength. And here's another sighting, and here's another sighting, and here's another sighting. So one of the things that Don and Dieter and this group have done is said, well, these access points, these sightings for these access points are probably along a road because people generally travel along roads. So let's take those GPS values and normalize them so that they're along the closest road. This is this graph-based Bayes network approach. The other thing that you can do that gives you higher quality GPS readings is you note when you make a turn. And all of a sudden, you're able to sort of compare the GIS data and your GPS data and correlate them and get an offset in one direction. So you almost have sort of a differential GPS capability by combining maps and GPS readings. And this isn't absolutely a new idea. Actually, the car-based GPS systems tend to do this a lot. You see snap to roads. But it does add to the accuracy. The other thing that you could do is you can learn simple models of AP and antenna propagation. And I think what this is basically showing is that using a number of data cleaning techniques and aggregating techniques over many different sightings, you can get a closer and closer approximation of where these access points should be positioned, and that in turn will provide better positioning for the clients. A lot of this work comes out of the robotics research area. That's where Dieter is his research area. So it's sort of interesting that robotics mapping and real-world mapping are coming together. So the other thing, there was this question about, well, what do you do when the war drivers stop war driving? So this is the problem, that war drivers aren't going to provide enough information to map all the access points in the world. So our idea here is to say, well, don't just use war drivers, but use everybody who has a Wi-Fi device and do a kind of distributed sensing project. So the idea here is that whenever I have my device with me, currently this Windows XP device is always listening, and actually always tries to connect to some access points, but it's always listening. And if you kept a log of when you heard an access point and the time, it might hear an access point T1 that is in the database, and so you know its GPS coordinate. It might hear an access point T2 that isn't in the database, and then at T3 it might hear another access point that is. And the idea is, approximate that middle access point, the location of that middle access point. It's all based on statistics, so you make a general assumption about motion models, and you say it's probably in the same country. High certainty, it's in the same country. And then, it's also probably in the same city. It's probably also in the same region. And you can get a pretty good idea of where these are, especially when you start thinking about doing this across hundreds or thousands or tens of thousands of users that are contributing these sightings. And so you can think of the GPS war driving as like the skeleton that you build out. And then this information that's coming from just everybody who has a Wi-Fi device is putting on, the meat on the bones. And one of the research questions is how much skeleton data do you need in order to converge on the other data? So how much positioned access points do you need so that you can then start positioning these unknown access points in a reasonable amount of time? So another aspect of this back-end database is, sort of the data model here. You could have a single centralized server, you could have a server farm, or you could have some kind of distribution. And one of the things that I am actually keen on is doing this in a distributed model. So instead of having a single mapper service, you have many different servers that are out there. And we do something called distribution for trust, which means that we have one of these mapping services that runs at UW, one that runs maybe at Google, one that runs at Intel, one that runs at San Diego. And each organization trusts, the people in an organization tend to trust the organization. And so they're willing to upload their war drives into that organization's service, which will then aggregate and sort of mix this data around and basically hide that personal information from the world at large. So I call this distribution for trust. So I put the second item first because I'm a trust. I believe that trust is one of the more important problems. The other reason to have a distributed system, sort of this back-end peer-to-peer network of these servers in a service, is because it does take a lot of computation to do this processing, and it's unreasonable to try and put it all in one server. So we have some challenges here. I'm not going to read them off, but basically they're motivating a design that uses distributed hash tables and sort of looks like a distributed, one of these peer-to-peer distributed file systems that are out there. So I want to end by talking about growing the user community. I said again, project is open source. You can go to our website and download, the executables, but also download the source. It's collaborative. We have our first Beacon location database is already live, and we're trying to bring up some of these other database sites. We have some courseware that's sort of evolving. Gaetano Borriello is teaching a course at UW on location-based applications, and he's using this toolkit. So it's sort of the first class. So in conclusion, we have this project, Place Lab, providing global indoor-outdoor Wi-Fi positioning, sort of good enough positioning, but very low cost. And we're using this as a way to bootstrap those large user communities to use, create, and share location-enhanced web services and local applications. And so, one of the things I'm doing here today is having the discussion about, research collaborations or collaborations with Google. And, just sort of I threw up on the list some of the interesting things that are going on here is local search. What would local search be like integrated with a local positioning capability? How would you do that in a toolbar with user interfaces? There's also sort of a group of users who are trying to geotag their web pages. In other words, not just use address blocks, but trying to be more specific, as well as this area of location-aware services. So local search is one service, but I think there's a number of them out there. So thank you.